So we're going to take this, we're going to graph it, and we're going to analyze it a little bit. First of all, what's the parent function? And what would b be in this case? 3. So yeah, the parent function would be f of x equals 3 to the x power. So what does that plus 1 up in the exponent do? Yeah, that's a horizontal shift. Because it's almost like, you remember when we did this before and we had like x plus 1 squared, and like it was on the inside parts that made it horizontal. Up in the exponent's like the inside part here. So down there the 3 would be like the outside? Yeah, so like if I did 3 to the x plus 1 like that, then that would be a vertical shift. See the difference? All right. So the transformation is, whoa, your other left. There, one to the left. So let's graph the parent function, and then we'll graph g, and then we'll talk about a couple things. So first of all, the parent function so that's f. Keep in mind, I generated these because 3 to the 0 is 1, 3 to the first is 3, 3 to the second is 9, 3 to the negative 1 would be 1/3, etc. So those are the points I drew to get that curve. Well, if I'm translating that 1 to the left, all I got to do is take all these points and shift them over 1. Like so. So the red curve is g, the green curve is the parent. So obviously, due to the translation, that no longer has the same y-intercept. And remember, last week we looked at a bunch of exponentials, and they all had the same y-intercept at 0, 1. But because of the translation or the shift, that doesn't have the same one. Does it have a horizontal asymptote? Where? There you go. And remember, I'm going to be extremely picky on that, especially on this next test. So the horizontal asymptote is y equals 0. What's the domain? What? Yeah. So negative infinity to infinity would be the domain. Just think about it. That's the domain of any exponential function, and if you take negative infinity to infinity and you shift it to the left one, that's still negative infinity to positive infinity. And the range? 0 to infinity. Which makes sense because the original range was 0 to infinity. And if all I did was shift left or right, I didn't shift anything up or down, so that's not even going to affect the range at all. Okay. Let's do another one. We ready? All right. So let's do h of x equals 2 to the x minus 3. So what's the parent function? Yeah, 2 to the x. Somebody I haven't heard from yet, what happened to it? Where? It's not up tree, down tree. Remember, you don't have to worry about doing an opposite thing when it's vertical. Yeah. So anyway, so this would be 3 in the downward direction with a vertical shift. Now, before we graph it, let's consider what that would do to all the stuff we did on the other one. So we looked at horizontal asymptote, we looked at range, we looked at domain, right? Let's look at domain first. So if we do the domain, what was the domain of the original? What's the domain of the parent? Yeah, all real numbers, negative infinity to positive infinity. So if I take that and move it down 3, does that affect the domain? No. So the domain would be negative infinity to positive infinity. All right. What's the original range? Say that again. 0 to positive infinity. If I take that and move it down 3, yeah, that would be negative 3 to positive infinity. And if I take the horizontal asymptote, which would have been y equals 0, that would be y equals negative 3. Ah. And let's see that reflected, not reflected, but not literally reflected, but let's see how this is represented with the graph. So anyway, yeah, because it's definitely not reflected. The graph isn't. Oh, fail. All right, so let's scoot this down some. All right. So if I draw the parent function, that's f. That's y equals 2 to the x. So I'm going to take everything from that function and move it down 3. So you can see how the range is affected and how the horizontal asymptote is affected, because the horizontal asymptote is right there. Make sense? That's one of the things that's going to be on your next test, is understanding domain and range of exponential functions. Not the test this week, but the test, the chapter 4 test. By the way, just giving you a heads up, the chapter 4 test has a calculator part and a non-calculator part. This would be something you'd find on the non-calculator part. Because honestly, what would you use a calculator for there? Now don't worry about that, because right after we take this test, I'll post the chapter 4 practice test, and you can see exactly what's on the calculator part and what's not on the, or on the non-calculator part. And you can prepare for it accordingly. It's not something to worry about so much, because a lot of the non-calculator stuff, you wouldn't really use a calculator for it anyway. So it's really not that big of a deal. Okay. So now that I've preached on that, I'd like to talk about the natural base. Has anybody ever heard of the number E? Yeah, has anybody ever used natural log ln in Algebra 2 or in other classes? Well, anyway, E is actually considered to be a number. The reason why it's E is because the guy who came up with it, or the guy who decided to give it a name, his name started with E, so his name was Euler. He was Swiss, but he was from the German-speaking side of Switzerland. So the Germans pronounce EU as Oi, as in like, you know, Deutsch. So literally the Germans call it the Euro instead of the Euro. But anyway, I digress. So E is approximately equal to 2.71828182 and some other stuff. It's similar to pi in that it doesn't ever repeat and it doesn't ever stop. It just keeps going with no noticeable pattern. Now you might wonder why we would ever concern ourselves with this number. I can tell you that it has very, very nice calculus properties. And that's all I can tell you because I'd have to teach you some calculus in order to understand why it works the way it does. But it's a very, very nice number to work with from a calculus perspective. All right. Now I'm going to show you an example out of the book. For those of you that are watching this video, this is on page 418 in the textbook. Change screens. All right. So, any idea what that is? That is a gray wolf. Insatiable killer. That's the reputation the gray wolf acquired in the United States in the 19th and early 20th centuries. Although the label was undeserved, an estimated 2 million wolves were shot, trapped, or poisoned. By 1960, the population was reduced to 800 wolves. This figure right here shows the rebounding population in 2 recovery areas after the gray wolf was declared an endangered species and received federal protection. So you got the Western Great Lakes region, the Northern Rocky Mountains region. Apparently in 1979 there were 2 wolves. Those 2 wolves got busy, I guess. Because later on the population rebounds nicely. Either that or different wolves came in. I don't know. We're not gonna go into great detail there. That's dangerous territory. I'd probably be fired for that. But anyway, so anyway, the exponential function f of x equals 1.26 e to the 0.247x models the great wolf population of the Northern Rocky Mountains. F of x years after 1978. If the wolf is not removed from the endangered species list, and trends shown in that figure continue, project the population in the recovery area for 2010. Yeah, this book is older than 2010. That's why it wants you to project, even though 2010 has already happened. All right. So, I wonder if this is still recording. Oh, just barely. So anyway, we'll set this up after this video is done rendering.